Okay, let's take a look at this example now. Now the trick with this is we are going to consider the rope and pulley system together as being our free body diagram. So I'm drawing a little box, an imaginary box. And this is a technique we can use all the time in figuring out free body diagrams. A free body diagram doesn't have to be of something real. It can be imaginary lines that divides one area of space from another area of space. So we have the pulley 100 pounds down. Some tension off at this direction. And a force at the pin A. So we have three unknowns, tension, AX, and AY. And now, the reason we don't consider the rope and the pulley separately is because the rope's force on the pulley is complex. Looks like this. But the pulley's force on the rope is equal and opposite. So these cancel out. We don't have to worry about this stuff. They're internal forces, internal to our free body diagram. The system, internal to the system we've defined. Okay, let's go on. We're going to take a look at, well, here's the picture again, and tensions. Okay, now take a look at the moment first. The moment has to be equal to 0. It's 100 times a half minus t times a half, which means t has to be 100. That's one of our rules, is that when a rope goes over a pulley, the magnitude of the tension remains unchanged. This is why, right there. Okay, F sub x, we have t sine 30. So t sine 30 here, and minus a sub x here gives us 0, so a sub x is 50. And then a sub y. We have negative 100, negative t cosine 30. Here. Negative 100, negative t cosine 30, plus a sub y has to sum to 0. So a sub y is 187 pounds. Okay. 2 and 3 force members. I've already talked about this. We've talked about it a couple times now. That to be in equilibrium, the forces have to be collinear. Collinear is not enough. FA has to be equal and opposite to FB also. But this helps you eliminate a force. You have X and Y components of A and B. All you need now is just one number, the tension between here. 3 forces. They must be concurrent or parallel. Parallel. So to be in equilibrium. So concurrent means the lines of action all go through the same point. Parallel would mean this situation right here. Why is that so? Any 2 forces will meet at a point. Now, we add a third force to the system. If the third force does not go through that point, then you're going to have a net moment. The sum of the moments is not going to be equal to zero, and the thing will rotate. Your system will rotate. The moment can only be zero if all three forces, the line of action for all forces, passes through a single point. It can also be zero if the forces are parallel. Okay. So these are ways to reduce your equations from a large number to a small number. These rules that we're learning. That's why we go through them. So how would we think about this problem? So we have a lever and somebody's pulling on it with 400 newtons. Determine the force on of the pin on lever A. There we go. We want to know this. Well, how are we going to sort this through? The forces have to now one item is that the forces have to be coincident at point O. So this will be point O right here. So now these two forces hit this, and we've got it solved. So we have a force here, and that force has to be collinear. So I've drawn a straight line, sketched a straight line through point O. Let's see. We have this force here acting on ABC. We're looking at the free body diagram of ABC. This force here, well, guess what? Now we can figure out the angle of A. We don't know the magnitude of A yet, but we do know the angle, because this force now has to be collinear with this point O. So if we find point O, which it's at 45 degrees, 0.2 meters here, 0.2 meters here, 0.5 meters here, 0.5 meters. And then A is 0.4 meters to point O, and then 0.5, 0.7 meters up. Okay. So now it's pretty much just getting the angles all right. The angle F. Let's see. The line of action of FA, and let's see. Yeah, FA is the vector of point A. Vector acting on point A. The line of action, 0.7 over 0.4. This will give us theta. Okay. Now we have a new diagram. And using force equilibrium, the FA cosine 30, which is cosine 60, excuse me, cosine 60.3. This is the x-axis direction. That's positive. We got a negative F cosine 45, and then a positive 400 equals 0. And then FA sine 60.3, the up and down portion, minus F sine, F is going down, so it's a negative sign. And now we can solve for everything. Yeah, anyway, it's calculator crunching now, and you guys, I'm pretty sure you can get this. Okay, 3D supports, on to 3D. And I'm going to pick that up in the next video.